Hey everyone, and welcome to this explainer. Today, we're totally cracking open the black box of recurrent neural networks, or RNNs. If you've ever wondered how AI actually manages to read text, translate languages, or just generally understand context over time, well, you're absolutely in the right place. We're going to break down the exact mechanics that make all this sequence modeling possible. So, here's our game plan for today. We'll start with the power of prediction. Then, we'll compare different neural networks. After that, we'll check out some real-world RNN applications, dive under the hood to see how their memory works, and wrap up with the challenges, specifically gradients and tan. Let's jump right in. All right, part one, the power of prediction, intuition first. Before we even touch a single algorithm, let's actively challenge your baseline intuition about time and data. Consider this core question for a second. Given an image of a ball, can you predict exactly where it's going to go next? I mean, it seems like a really simple proposition, right? But it actually highlights the sheer impossibility of predicting the future when you don't have any historical context. Think about it. With just a single static image, literally a snapshot frozen in time, this blue ball could move up, it could drop down, or it could dart off to the left. We have absolutely no idea, because we're missing the crucial element of time. Without sequential context, any prediction you make is just a wild guess. But watch what happens here. When we start seeing the previous states of the ball fading in right behind it, suddenly that sequence gives us a trajectory. Our brains naturally almost instantly predict the path forward. And you know what? That perfectly mirrors the exact sequential data problem that recurrent neural networks are explicitly built to solve. They don't just look at a single static snapshot, they look at the whole sequence. Moving on to part two, comparing neural networks, finding the right tool. Let's look at how different AI architectures have evolved to tackle very different types of data. Okay, let's dive into this and compare the distinct structural blueprints of three major networks side by side. So we've got the convolutional neural network at the top, a deep artificial neural network on the bottom left, and a recurrent neural network on the bottom right. Just visually, you can notice how fundamentally different their internal wirings actually are. Let's break those blueprints down functionally. Artificial neural networks, or RNNs, they process information straight through their interconnected layers. That makes them super great for general tasks and pattern recognition. Then you have convolutional neural networks, or CNNs. They use specialized layers to detect features in images, like edges or shapes. But recurrent neural networks, they are the absolute hero for sequential and time series data. Why? Because they have connections that literally loop back on themselves, which allows them to remember previous information. It's a real game changer. All right, part three, real-world RNN applications. Beyond the bouncing ball, we know they handle sequence, but what does that actually look like in practice? Well, sequence modeling architectures offer just incredible flexibility. You can match different amounts of input data to output data in all sorts of configurations. One-to-one, one-to-many, many-to-one, and even many-to-many. Honestly, this adaptability is the true superpower of the RNN. To digest that into something a bit more concrete, here are some really common applications mapped out. We use RNNs for binary classification, generating image captions, sentiment classification, like figuring out if a review is positive or negative. They're also used for machine translation and named entity recognition. So basically, anytime you use an app to translate a sentence from English to French, you are relying on an RNN to process that sequence of words. Which brings us to part four, how RNN memory works under the hood. Let's zoom way in from those macro applications right down into the exact micromechanics of how an RNN manages to retain that past information. It all really boils down to this vital concept called the hidden state. Think of the hidden state at time t as the ongoing internal memory of the whole network. It calculates its current state based on just two things, the current input it's receiving and the hidden state that was passed down from the previous time step. Let's just walk through this step by step so it clicks. First, the network takes the current input, say a mathematical vector that represents a specific word. Second, it reaches back and retrieves the previous hidden state. Third, it essentially glues that input and the previous hidden state together into a single combined vector. And finally, step four, it passes that new vector through a tan activation function, spitting out the brand new hidden state. So ultimately, the hidden state acts as the neural network's memory. It holds on to information from previous inputs. This looping mechanism is what carries the context forward. It's literally exactly like you remembering the beginning of this sentence so that you have the necessary context to understand how it ends. Makes sense, right? Now for our final section, part five, challenges. gradients, and tan. Because as it turns out, maintaining an artificial memory over long sequences is mathematically really difficult. The biggest villain we run into here is a phenomenon called vanishing gradients. Let's just strip away the jargon for a second. A gradient is essentially the error signal the network uses to learn. When the network tries to update its weights, this gradient signal can actually shrink as it travels backward through time. And if it shrinks too much, well, the value becomes negligible, meaning the network effectively forgets how to learn from the older data in that sequence. This is exactly where the tanh activation function steps in as a vital safeguard. With tanh, the network introduces this crucial nonlinearity to learn complex patterns, while actively squishing the mathematical values so they don't just explode out to infinity. Without tanh, actually, scratch that, if you took tanh away, the RNN would literally devolve into a basic linear model. It would completely lose its ability to process complex, time-dependent sequences. It basically loses its entire grasp on time. Which leaves us with a pretty fascinating limitation to ponder. If even well-designed basic RNNs eventually forget early data because of vanishing gradients, what massive architectural leap will AI need next to achieve true, flawless long-term memory? Well, there is a whole world of advanced sequence modeling beyond basic RNNs built to solve exactly this problem. Keep that question in mind as you continue your journey into natural language processing. Thank you so much for joining me for this explainer, and keep learning.